So usually when I do my 5K runs, I try and maintain a pace of about 5 minutes per kilometer for my 5K. And for Imperial viewers, that's about 8 minutes per mile for a 3 mile run, more or less. Now, you would notice that there's some oddly round numbers here, right? 8, 3, and 5. And you would notice another pattern with these numbers, which is that 3 plus 5 equals 8. Now, if you consider this to be just a coincidence, hear this out. 5 plus 8 is 13, and 13 miles is how long a half marathon is, and 8 plus 13 is 21, and 21 kilometers is about 13 miles, so it's also the length of a half marathon, more or less. Now, you might already recognize this, and it turns out that 3, 5, 8, 13, 21 are members of the famous Fibonacci sequence. So it's a number sequence where you get a certain term by what is called a recursive relation. So you add the last two terms, right? So 0 plus 1, and it gives you the next term. So it gives you 1. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on, right? So this is the recursive relation that builds this. And if you take the ratio of these numbers, right? So, for example, you take 1 divided by 1, or 2 divided by 1, or 3 divided by 2, or 5 divided by 3, you would notice that this ratio approaches a mathematical constant, which is famously known as the golden ratio, written as phi, and it happens to be really close to the conversion factor between the mile and the kilometer, right? So this number sequence, the ratio of its terms happens to align pretty close to the conversion factor, which is why you see that, the further up you go, the better your conversion is. So, well, 13 miles is 21 kilometers. It's pretty good conversion. But the Fibonacci numbers are not really very special in that regard. For example, if you take what is called the Lucas numbers, so instead of going 0, 1, 1, 2, 3, what you do is you swap the 1 and the 2. So you start with 2 and 1, and you build up the series with the same logic. So 2 plus 1 is 3, 1 plus 3 is 4, 3 plus 4 is 7, and you look at the ratio of the numbers, it also approaches phi. And on top of, in this way, approximating miles and kilometers, Lucas numbers happen to be really nicely used in the field of cryptography. Okay, one instance where you can see this, and why this may be true, is look at this particular property of Lucas numbers, right? So starting from index 0, so this is the 0th Lucas number, right? If you take any prime p, so take 5 for instance, 5 is a prime number, so it has no other factor other than itself and 1. So you took the 5th Lucas number, so L0, 1, 2, 3, 4, 5. So the 5th Lucas number is 11. And what you can get if you divide 11 by 5 is the number 1. So 1 is the remainder when you divide 11 by 5. Similarly, the 7th Lucas number divided by 7 also gives you the remainder 1. And this happens to be true for all prime numbers. So for all primes p, the pth Lucas number gives you a remainder of 1 when divided by p, which can be written as 1 mod p. Okay. When you combine Lucas numbers with what is called the Miller-Robin primality test, you get a probabilistic primality test, which has no counterexample. So a probabilistic primality test is a test that likely tells you whether a number is prime or not. And for all the numbers we've checked, it exactly tells us whether it is prime or not. But we haven't proven that that is true for all numbers. It's so useful that it is used in softwares like Maple, Mathematica, and Java. Okay. So Lucas numbers, really cool. Okay. But it turns out that not only the Fibonacci numbers that start with 0, 1, or the Lucas numbers that start with 2, 1, but really almost any two numbers that you give it as seeds, including real numbers that are not just integers, the sequence for almost all seeds happens to get this ratio that tends to the golden ratio as you push the numbers higher up the sequence. Okay. Now I say almost because there are some special set of numbers that do not do this, and it might be a nice challenge to think of what those numbers are. And we'll perhaps talk more about that later. But let's first see why this may be true. Okay. So we're going to prove that for any sort of starting point, your sequence has the ratio of the consecutive terms limiting to the golden ratio. Okay. So let's consider this generic sequence A0, A1, A2, A3, A4, A5, and so on. And let's assume that the ratio that the terms have for large n is R. And the point is we want to prove that R is the golden ratio. Okay. So we define the recursive relation for our sequence. That's what will govern our sequence. That's what is common among all the sequences we talked about. And what this means is that not only is an over an minus 1 r, but also the pair of terms right before that, because n is large, that should also be r, right? And what you do is you multiply an minus 1 times an minus 2 on both sides. So you cross multiply, and you get an times an minus 2 is the product of the middle terms with itself. And you can use the recursive relation to expand on an, and that gives you the following. The last thing that you want to do is to see from this equation that an minus 1 is equal to r times an minus 2. And you substitute that in for an minus 1. Right, so you get an equation in an minus 2 and r. And it turns out that you can cancel all these an minus 2's, and you get an equation in just r, right? And if you want to write it in standard form, you just write it here. You just get that r squared minus r minus 1 is equal to 0. So you just take this the other side. It turns out that this quadratic has these two solutions. Okay. Now this guy is positive and this guy is negative. And remember, r is the ratio between the terms. In all these series, you can see that eventually the numbers end up having the same sign. So the ratio of these numbers better be positive, right? So most series that, or all series that we've concerned, all the series in our minds so far, have the ratio being positive. And so this is the solution that we consider. And well, this happens to be the golden ratio. And so there you have it. All the series that we've looked at, given the assumption that we've made that we have likely slipped under the rug, the ratio of the limiting terms happens to be phi. And we assumed nothing about the starting points here. Another interesting note about phi and this -1/phi is 1 minus phi. You can see that the decimal places here are the same. So it just comes from this quadratic equation. If you rearrange this, you'll get the same quadratic. Okay. Oops. Sorry for that. Okay. Now, what you want to do is you want to see that, okay, sometimes you would want to get the nth index, right? Or rather, at the nth index, sometimes you would want to know what is the anth number, right? For example, if you want to know if 87 is a prime, right? The 87th Lucas number, when divided by 87, gives you 62, which is not 1, and so it's not. Okay. Yeah, what you can do is you can, because cryptography, at the heart of cryptography are large primes, you can do something similar, or you may want to do something similar for very large primes. Say you want to know whether, I don't know, 2 to the 51 minus 1 is prime or not. So you would want the 2 to the 51 minus 1th Lucas number. But even for 87, you want to do 87 of the algorithmic additions, but this is just not possible for 2 to the 51 minus 1. And, well, this is not exactly the reason you would want to know the nth Lucas number. Even that is inefficient, but you might want to know it for whatever reason. And it turns out that there is a way to know the nth number for any of the series in our hand, as any of the sequences in our hand. Okay, so the way you do it is you realize that the two solutions that we had to the characteristic equation in R, phi and the other thing is called psi, which is defined as -1/phi. So the other solution that we had, you can construct two sequences that are pure powers of these numbers. So you can consider alpha, which is just a geometric sequence of phi, and beta, which is a geometric sequence of psi. And you can, because it was the solution to this characteristic equation of the sequences defined by the recursive relation, you can consider the general solution to be a linear combination of the terms of these two sequences. Okay. For example, the Fibonacci sequence, if you work out these two constants with your initial two seeds, you will notice with a few calculations that these two weights are negative of each other, and their magnitude is 1 over the square root of phi. So this is the formula for nth Fibonacci number, and it's called Binet's formula. You can do the same for other sequences. So Lucas numbers, they have a really nice formula because the coefficients are just 1 and 1. If your sequence starts with something funny, so 6, 7, then you have some other weird numbers, but the point being that it's just the powers of phi and psi weighted by some constant. Another interesting fact is that you can write these sequences in terms of each other. Okay. Now, an interesting reason why you might want to know the nth Fibonacci number, for instance, goes way back to ancient India. So, ancient Indian scholars, they really loved music and poetry, right? So, they had this problem that if you had a song with n beats, so here I have 6 beats, and you want to make the rhythm for the 6 beats using a short sound and a long sound, which lasts 1 and 2 beats each, respectively. They wanted to know how many different rhythms can they make. So you can go short, long, or short, short, long, short, short, or long, short, 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 short. And it turns out that if you work things out for small numbers, so for just one beat, there's just one way you can do this. You can have just the short beat. For 2 beats, for 2-beat rhythms, you can have 2 short beats or 1 long beat. And for 3 beats, you can have short, 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 long, or long, short. And it turns out that for n beats, you have the nth Fibonacci number. Okay. So this sequence tends to be the Fibonacci number. Another extension of this idea can be used for domino tiling. So say you have a grid of 2 by n tiles, and you want to tile it with a horizontal or vertical domino. It turns out that for the length n of the grid, there are the the number of ways you can do it is the nth Fibonacci number. So in this case, it'll be 8 different ways. Okay. So that's that. And I could end it here, but there's another thing I want to talk about the Fibonacci numbers, which is how can you compactly shrink this entire sequence in a nice way. And it's a little bit out of bounds of this video. It's a little bit of a detour, but it's so beautiful that it'll be a shame to not mention this. Okay. So to do that, we first look at another sequence, which is the powers of 2. Okay. Say I want to package this sequence into a function. One way I can do this is by just assigning these numbers as coefficients of powers of x. Okay. So the 0th number is the coefficient of x to the 0, and so on and so forth. And you can see that, you can basically take any sequence, so 1, 2, 3, 4, and you can package it as a function. Now, sure, like this is nice, but this is not compact. Like, why would one do this? You can realize that this is what is called a geometric series, right? So it's sum of terms of a geometric sequence where the terms are just and a ratio of a ratio r, okay, and you can figure out a formula for a geometric sum where r has certain properties. So in our case, we can represent this geometric sequence, which has r being 2x, as just 1 minus 2x. Now that is compact, and these are just equivalent. Okay, so somehow the function 1 over 1 minus 2x represents or encodes within it all powers of 2. And that's really interesting. Now, if you don't know what a Taylor expansion is, it's just a way to express any function or several functions, certain functions, as polynomials with certain coefficients. Okay. And a lot of these nice functions that we see in school can be represented as this expansion of just a polynomial. Okay. So yeah, you can have the powers of 2 be encoded in this number. Now we want a function that encodes the Fibonacci sequence. And it's 1 over a polynomial. And a nice guess would be to consider the characteristic equation that we saw, which was x squared minus x minus 1, which was the characteristic equation for phi, whose roots are phi and psi. And you can see what the Taylor expansion of that reciprocated polynomial is. And it turns out that it gives you something very similar to the Fibonacci sequence, except it's missing the zero term, and it has some negatives and positives and so on, right? And it turns out that if you just add an x and do some sign flips, you can fix this. Okay. So this is the correct thing that gives us the Fibonacci sequence. Right? So this encodes the Fibonacci sequence. Okay. Now, we haven't talked about why this does that. And there are many different ways to do it. But my favorite way is the one that involves constructing the Pascal's triangle. And if you don't know about Pascal's triangle, see it in a bit, but it's super elegant. But before that, one interesting thing that you can do with this is plug in the number 1 over 10 into this, and what this gives you is just coefficient terms in the decimal places. Oops. Yep, this should be 0, 0, and this should be 0, 0, 0. Okay, never mind. But yeah, what this tells you is that if you look at, for example, the number 1 over 89, in some way it encapsulates the Fibonacci sequence as just its decimal places. So 0, 1, 1, 2, 3, 5. It breaks down after that because then you get units carried over and so on, but it works so efficiently. It's magical. So why x over 1 minus x squared? To do this, we again use the geometric sequence thing. So 1 over 1 minus r is just 1 plus r squared plus r cubed and so on. And it turns out that if you consider this thing as r, you can get the following sum. And if you factor out an x to the k from this, this is what the sum becomes. And if you look at what the sum is for k equals 0, 1, 2, 3, 4, you get to see some really nice pattern. You get the following sort of triangle. Now, Pascal's triangle is this shifted here, centered, but you can already see it. So the number over here is basically the sum of the numbers above. So this number is the sum of the numbers above. So in this case, it's the number up and to the left. But in the actual Pascal's triangle, it's 1, 1, 1, 2, 1, 1, 3, 3, 1. So you look at the numbers exactly above it. Okay. And if you add the diagonals, you get the Fibonacci sequence. How cool is that? Now, there are ideas out there that, the Fibonacci numbers and the golden ratio, the golden spiral, they're everywhere. And to be honest, I don't know about everywhere. But what I can say is that they are sort of a gateway to look at very interesting realms of mathematics, which are really, really beautiful. So yeah, I hope you enjoyed this video. I hope you learned something. If you took away something, hope you had fun. And yeah, stay curious and may the kid remain.